All right, I guess we'll go ahead and get started. And folks at home, you're good, you can hear. Let me know if you can't. Say something in the chat. Good, yep, okay. So before we start in on the science, a little bit of logistics. There is an exam scheduled for February the 27th. That is Saturday next. Some of you have asked, are we likely to get through everything in chapter 7 and 8 before the exam? And the answer is no. I wrote Practice Exam 2, which is now posted, by the way, based on the idea that we would. So there are some problems on Practice Exam 2 that we won't get to and you won't be expected to do prior to the exam. Of course, it would be lovely for me to tell you precisely what won't be on the exam, and it's difficult to say without knowing where we're going to be on Friday. I've typically spent maybe 6 lectures on the material in chapter 7 and 8. We're finishing chapter 6 and moving on to 7 today. So that would put sort of 4 out of 6 possible lectures on chapter 7 and 8. Some things I may not cover in as much detail. You're basically going to have to trust me that I won't test you on things that you're not prepared to answer. I realize that that's uncomfortable, and I'll try to give you more updates as we get closer to the exam date as to what we're not going to get to. But probably the later you get in Practice Exam 2, the less likely it is that we're going to be getting there. Chapters 4 and 5 and 6 will certainly be on the exam. We'll probably do quite a bit of substitution reactions and maybe a little bit of elimination reactions. So that's what I can tell you at this point. We could, in principle, push the exam backward, but that's a mixed bag because it gives you more time, but then the exam would cover more material. So kind of a toss-up. I think for now we'll stick with Saturday. The format will be the same. I don't yet know how many questions will be on it. That will depend on how many I'm able to write between now and then. But the format will be the same, multiple choice. It will also be a time limit. It will also be open book like last one was, but you have to do your own work and not work with others. Scheduled for next Saturday only, that is true. As before, if you have exceptions through the UAC, I will build those in already. So if you want to check with me and confirm that I've done that as the exam gets closer, you can. If that presents a hardship for personal or other non-emergency reasons, feel free to contact me and we can see if we can work something out, though I can't guarantee anything in advance. So, anything else? Yeah.
Will there be specific questions from like last exam?
Will there be specific questions for last exam? How do I answer that? OChem by its very nature is cumulative, so you can't easily forget everything from the past and still do well at what's coming in the future. I have in the past rehashed old questions to give folks a second chance on demonstrating understanding or performance. I'm not sure how likely that is. Nevertheless, if you've got limited time, is it worth all your time to spend going back and relearning the pKa stuff or focusing on the new stuff? You'll have to assess that, but my guess is the newer stuff's more valuable. Now watch me throw a curveball that makes it so that what I said doesn't apply. Yeah, I think in general, your best bet, you're going to need previous stuff. You're going to find in chapter 7 and 8 that we rely a ton on pKa intuition and things we learned in chapter 2. So as you need it, certainly go back and review, but staying current is probably more important. Other questions? Okay. Well, we're going to get into now how reactions happen. We talked about thermodynamics last time. Today is about kinetics. And I need to press, nope, it's been recording, good. So when we talk about reaction kinetics, we're basically asking the question, what happens when, in what order, and how fast? Another way of talking about kinetics is to think of something called a reaction mechanism, which is a short one-word thing for saying what happens when and in what order and how fast. So it's probably easiest to talk about this using an example. So this is a real reaction, and people have studied it before. I don't have the actual real data in front of me, but this kind of reaction is known and understood pretty well. And so what I will tell you about this reaction is going to be pretty accurate in terms of what you could realistically expect to happen in the lab. And I think I want to draw out the bonds in this molecule to make our discussion a little clearer. Okay. So this is called a substitution reaction because we're replacing iodide with cyanide. We're breaking one bond and we're making another bond. The bond that we break is a carbon iodide sigma bond where the carbon is sp3 hybridized. The new bond we make is a carbon-carbon sigma bond, carbon cyanide sigma bond where the carbon on one side is, excuse me, sp3 hybridized. And I will tell you for future purposes that the Cn minus is our nucleophile and the methyl iodide is our electrophile. And you should probably already be thinking, you know, in terms of the nucleophile, what's the HOMO, in terms of the electrophile, what's the LUMO, though we probably won't get into that very much today. So if we think about whether this reaction is downhill or uphill in energy in terms of its thermodynamics, we would compare the fact that we've got to break the carbon iodide bond and make a carbon-carbon bond. And if you go back and look at the table of bond strengths in your book, you could draw the conclusion that the new bond we make is stronger than the old bond that we break. And so that would tell you that this reaction is likely downhill in energy. That assessment doesn't capture the difference in stability between Cn minus and I minus. To get that and factor it in, we could think of the pKa of the conjugate acid of each negatively charged thing. HCn's pKa is 9, whereas HI's pKa is like minus 11. So another huge multiple orders of magnitude difference in stability, which leads us to believe that not only are we making stronger and more stable bonds, but we're also making let's say, more stable anions as we do this reaction. So we expect this reaction to be exothermic and downhill. Now that's thermodynamics, and that tells you why the reaction happens. But now we want to worry about what, or rather how it happens. We already know what and why, but how is the question. And we're going to try to approach this discussion today not from the standpoint of already knowing what the answer is, which I do, but from how you would try to figure out how the reaction happens, what kinds of questions you would ask, what kinds of hypotheses you would make, and what kinds of experiments you would propose to test those hypotheses. So let's think of a few scenarios, or maybe in more words, mechanistic hypotheses that we could make for how this reaction happens. We know we've got to break a carbon iodide bond and make a carbon-carbon bond. So scenario one might be that we make the carbon-carbon sigma bond first, then in a second step we break the carbon iodide bond. Maybe another extreme would be that we break the carbon iodide sigma bond first, then make the new carbon-carbon sigma bond. And then option 3 might be that we do both at the same time or in the same step. So a few options, and what we're going to do is we're going to think about what the intermediates would look like in this reaction, what the transition states might look like, and then how energy might vary as we go from starting materials to products. So I'm going to use some abbreviations today. Starting materials is just going to be a generic term for reactants. We'll abbreviate that with SM. Products, we're just going to abbreviate with P. And then intermediates, we're going to abbreviate with I. And transition states, we'll abbreviate with TS. I will say this again, but I'll point out now, people will always ask, what is the difference between an intermediate and a transition state? Intermediates are energy minima. They are in equilibrium with starting materials and products. You can observe them. Transition states are energy maxima. They are very short-lived, and you can't directly observe them. But you can infer some things about them and then do some calculations. Go ahead.
Can you stop a reaction at an intermediate?
Can you stop a reaction at an intermediate? Yes, if the various differences in free energy allow the concentration of the intermediate to be large enough at equilibrium. Sort of hard to do. You can often trap the intermediate as something else, but there are techniques we can use, mostly spectroscopic techniques involving shooting light at a sample, where we can observe an intermediate even if we don't isolate it. All right, so let's look at the first hypothesis. This one's kind of funny. We're going to first make the carbon-carbon sigma bond. So we'd start out with our starting materials and then make the new bond without breaking the old bond. And one hypothesis would be that you end up with some sort of arrangement like this, where Cn minus has already made a new bond, but the iodide bond hasn't broken. If I'm making formal charges here, I would say that carbon is negatively charged. That should make you uncomfortable. Why? Well, all chemistry makes me uncomfortable, says my son Jack, and that's fine. Why?
There's 10 electrons on carbon.
10 electrons, 5 bonds. You got yourself a hypervalent carbon, and we've been told not to do that. In practice, we've said that that's unreasonable before, because remember, carbon comes with 4 atomic orbitals, and that carbon can be involved in 4 bonding orbitals and 4 anti-bonding molecular orbitals. if you surround the carbon with 10 electrons, in terms of our model for bonding, that means you're going to have to populate an anti-bonding orbital, which seems like a bad idea. And that's a great way of looking at it. The other thing, the other explanation is just that carbon is so small that you can't get 5 different things around it close enough for all of them to be tightly bonded. There are examples, very rare examples of molecules like this, but it's very hard to get there. And it's because carbon's so small that once you surround it by 5 things, they're all far enough away that the bonds aren't very strong. So already we're not liking this mechanistic hypothesis. Presumably then we would go step 2 to products. And if we think about what the transition states would look like, transition states are involve incomplete changing of bonds. That is, if in this first step we are making, as we said in our mechanistic hypothesis, making the carbon-carbon sigma bond, then that process would be incomplete in transition state 1. What we might expect transition state 1 to look like is perhaps Cn minus coming in and looking like it was starting to make a new bond with carbon. As that happened, perhaps you have a partial negative on the Cn minus as the bond starts to form. And then you get to this intermediate. Some chemists will put transition state structures in brackets with a double dagger to indicate that it's a transition state. That's fine or not. I can't imagine asking a question where the whole point of it would be, do you recognize or use a double dagger properly? We've got way bigger fish to fry. The transition state maybe for the second step, this would involve breaking the carbon iodide sigma bond. And so perhaps this looks like you got the new carbon bond fully formed, and then iodide is leaving with a partial negative charge on it, and then products we've drawn before. Okay, so that's mechanistic hypothesis 1. Why are we spending time with it? Well, it's sort of an extreme, and it's one we can rule out easily because it just looks kind of dumb for reasons that we've already talked about in terms of bonding in organic molecules. Okay, so let's try mechanistic hypothesis 2, which is we're going to break the carbon iodide bond first. So starting material, break carbon iodide sigma bond, and we're going to get to an intermediate. I guess I should have pointed out that this is an intermediate. Starting materials, products. Our intermediate I, in this case, is going to be without the carbon iodide bond, but also we won't have replaced that yet with the carbon-carbon bond. So effectively, we will have a carbon that's only surrounded by 3 things. The carbon would be positively charged because iodide would have completely left already. We'll put it down there because it's gone. This intermediate is called a carbocation, and it's trigonal planar and sp2 hybridized at carbon for reasons that you should recognize already. What do I think in terms of the thermodynamics of that first step? Should it be uphill or downhill to go from starting materials to the intermediate I've shown you there? Uphill, okay? Or endothermic. Why? Because, like we learned last time about ATP, breaking bonds always is uphill in energy. The downhill part is where you replace the bond with something more stable. Only in this step, We haven't done that. We've just broken the bond. So yeah, that's got to be uphill. If we were to draw a transition state for this step 1, it would probably look like this with iodide on its way out. Now, I've had some people ask over the years, how could that even happen? How could iodide just leave? It's uphill in energy to do. And the answer to this has to do with thinking about bonds between atoms as being sort of like springs, okay? If you plot energy versus, say, carbon iodide bond distance, you see an energy well that looks something like this. At first, they're apart at infinite distance and they don't see each other. As they approach, you start to form a bond. And then as you get too close, energy goes up. And so the system will vibrate around this energy well as the distance between carbon and iodide shrinks and increases a little bit. So in a solution, molecules are bumping into each other constantly, and sometimes enough kinetic energy can be transferred from one molecule to another that the bond vibration starts to get large enough that iodide can escape. And it's not like iodide just decided to up and leave, it's just that that molecule got enough kinetic energy for that to happen. All right, we'll talk about this more, but this kind of thing does happen. It is slow because it's uphill in energy, but it is a reasonable possibility. Then we might predict in the second step, we're going to make the new carbon-carbon sigma bond. This should be downhill in energy, and delete that, don't need it anymore. This one probably looks like, I guess we should have put a partial positive on that carbon as the iodide is leaving. This one probably looks like we're just sort of the reverse of that first transition state where we're starting to make the new bond. Okay, and then we would go to products. All right, let's now think about, so far, how do you feel about reasonability versus the first one? We're at least not breaking any octet rules for second row elements, so looking decent. Let's consider, based on what we've said so far, how we expect energy to vary as the reaction progresses. And so we're going to introduce something called a reaction coordinate energy diagram. Reaction coordinate is a fancy word that just means reaction progress. Reaction progress, we can consider it generically, though you can measure it. It might be how far broken the carbon iodide bond is, or how closely to made the new carbon-carbon bond is. We're just going to keep it generic and a measure of reaction completion or doneness or something. We've said before that our products here are likely lower in energy than starting materials. And we've said, based on this discussion, that intermediate carbocation should be higher in energy than starting materials and higher in energy than products. As we said before, starting materials, products, and intermediates occupy energy minima. They are stable structures, or they have lifetimes where they can be observed. They occupy energy minima. So there's a high energy transition state that leads to, that is the energy maximum that leads to the intermediate. This is transition state 1. And maybe actually the intermediate is closer in energy to the transition state than I had originally drawn. And then in a second step, we increase in energy a little bit to go downhill to products. And this would be transition state 2. People have asked, okay, I get how it's uphill in energy because you're breaking a bond, but why do you go down in energy as going to the intermediate? This has to do with reorganization of the system. Look at this transition state. You've lost a lot of the benefit of the carbon-hydrogen bond, but the carbon-iodide bond, but the carbon-hydrogen bonds are still close to each other as though this were still sp3 hybridized, and there's some repulsion there. That gets relieved as you go down to the intermediate and you go to sp2 hybridization. Similarly, why, when we're starting to form a new bond, do we go up in energy a little bit? Same sort of thing. Before you get the full benefit of the bond, you start to have to distort again towards sp3 hybridization, bringing those electrons in the carbon-hydrogen bonds a little closer to each other. In general, we're going to see that reorganizing geometry always involves energy changes, and relieving electron-electron repulsion is always important. Okay, so other questions so far? Yeah.
So is this kind of like when you were showing the eclipse and the staggered conformation, how the energy levels change because of just the position of them? So is that why it goes up and down?
Yeah, so this is an energy diagram very much like what we saw before with eclipsed versus staggered. Eclipsed was a transition state, staggered was an intermediate, and energy's going down. The only difference is what's on this x-axis. For the conformations, it was dihedral angle. In this case, it's reaction progress. We weren't making or breaking bonds there, we are here. But other than that, it's analogous. So whenever bonds are formed or broken, there will be an energy requirement, yes. The relationship between starting material and products is going to be based on whether the bonds you form are more stable than the bonds you break. And then the positions of the intermediate is going to depend on the structure of that intermediate relative to the starting material and the product. Now that we have this energy diagram, we can talk about something called activation energy. And this is a concept probably you're familiar with from general chemistry. The activation energy is the energy required to go from a starting material or an intermediate over the next transition state. So going from starting material to transition state 1 is this energy difference I've drawn, and we'll call that activation energy 1. And then if you were to go from the intermediate through transition state 2, you're looking at this energy difference between intermediate and transition state 2, and we'll call that activation energy 2. And it's clear, at least in this case, that activation energy 1 is much bigger than activation energy 2. JJ has asked, does breaking a bond always take more energy than making a bond? Breaking a bond is always uphill in energy. Making a bond is downhill in energy. So in a situation where the activation energy for the first step is much, much greater than the activation energy for the second step, what this means is that the first step is way slower and the second step is way faster. All right? And this allows us to think about a concept called rate limiting or rate determining step. When the activation energies of two steps are different, only the slowest matters. The rate is determined by the slowest step. Okay? The analogy to this is we were once assembling lunches as a family on a Christmas Eve, and we had all these materials that we'd gotten from Costco, and we were organizing them and stuffing them in bags and whatnot. And it became very clear that I was the rate determining step, this may not be exactly how it imagined, but I'm imagining in retrospect, knowing myself, that I probably was the rate determining step. Because it didn't matter how fast the boys could pick up a bag of chips and stuff it in the bag, and it didn't matter how fast Amber could pile bread and jam and peanut butter in front of me. If making the peanut butter sandwich was the slow step, and who wants a peanut butter sandwich anyway, but if making that was the slow step, it didn't matter how fast everything else would happen. The overall rate was determined by the step that was the slowest. And in a lot of ways, it's similar in reactions. And so if the activation energy of the first step is a lot bigger than that of the second step, only the first step determines how fast the reaction is. I want to head off a question. Go ahead.
So I understand why the starting material to TS1 jump is bigger than the I to TS2, but how come the TS1 and TS2 aren't at the same level? Because isn't it the same conformation of hydrogens on both energy steps?
Yeah, so the question is why, it's a really great question, understanding why it's uphill to go to the intermediate, but why isn't it just as much uphill to go from intermediate to transition state 2 as it was here? The new bond that you're forming is stronger than the bond that you broke, and so that pays for this. And you're arguing correctly that there's the exact same amount of geometric reorganization there. You're paying for it more effectively because the new bond you're making is stronger, even at early stages. I think that's jazz hands explanation, but that's what I got. All right, where were we? So if only that first step matters in terms of the rate, we can actually make some predictions about how the rate of this reaction should depend on either of the starting materials. So you may have learned in general chemistry that for a single step of a reaction, you can write, if you understand the molecules that are involved in that single step, you can write a rate law for the reaction that depends on the molecules that are involved, okay? So what we're gonna say is overall for this reaction, the rate depends only on the process of going from starting material to intermediate through TS1. So let's go back and look at that transition state and look at who's involved. The methyl iodide is involved in that transition state, but not the Cn minus. And so the rate law we would write for that step is rate is equal to some constant times the concentration of methyl iodide. And we would leave out the concentration of cyanide because cyanide's not involved in that step. And that's the prediction we would make based on this energy diagram. Now, is that familiar to you? Are you okay with writing rate laws for elementary reaction steps? It can get way more complicated than this, but that's all we'll need to know. I do want to, just remember what I was going to say, I do want to head off a question that always comes about, well, what if the second step is higher in energy than the second transition state is way higher in energy than the first transition state? There are examples of that, and there are ways to deal with it. It involves using something called a steady state approximation, and the kinetics are fine, but it involves a little bit of algebra. We're not going to do that. For most of the examples we can talk about, there will be a single rate determining step. There might be a few steps in the front where we're doing some proton transfers to get the reaction going, but there really aren't going to be examples where we've got a second step that's like crazy high in energy. So though those situations exist, we're going to punt and not worry about them. Excuse me. All right. So let's think about what we might observe if we did some experiments. One experiment to do would be to keep the concentration of cyanide constant, and then vary the concentration of the methyl iodide, and then measure the rate. How do you do this? Well, there's lots of ways to do this. In a lot of ways, in many cases, you have some spectroscopic signal, NMR or infrared or UV vis, some kind of signal you can watch as a function of time and watch your product appear or watch your starting material disappear. We won't worry about the excuse me, the actual details of that. But let's just plot what we would observe if we did this experiment where we're varying methyl iodide concentration while keeping cyanide concentration constant. We try a bunch of concentrations, and if our expectation for this mechanism is accurate, this is what we would observe. This is called linear dependence of the rate on the concentration of methyl iodide, and it is evidence that rate equals K, rate constant, times methyl iodide. It is evidence that that rate law is correct or reasonable. I hate to say true, because in science we never prove that anything's true, and anybody that tells you different is selling something. In science, we only eliminate possibilities that are not true, and we show that data are consistent with a hypothesis, but you can never prove a hypothesis true. End temporary soapbox. So we would expect, based on this rate law, a linear dependence. Every increment that you increase methyl iodide concentration should lead to a corresponding increment increase in rate, and the slope of this plot would actually be the rate constant K. Questions so far? We'll call this linear dependence of rate on just the methyl iodide concentration a first order rate law, because there's only one concentration term in it. Another word for that is unimolecular. And the Apple Pencil's down to 3%, so I need to charge it for a minute while telling a story. What story am I going to tell? This is not a very funny story, but on Monday, when we were all off and you were all studying stressfully, I went out into the yard and try to do some yard work. We live in a neighborhood that's there's a street right in front of our house and then another branching street, and so the people are always coming and going, and the FedEx and Amazon trucks are constantly hitting tree branches from the two little trees that are in the parking strip. And I started to feel bad for them. At first I was annoyed that they were running into my trees, and then I realized it was probably my job as a good citizen to make sure that my branches weren't hitting their cars. So I went out with some pruning shears and some loppers and started clipping off branches, and one thing led to another, and I suddenly had these big piles of branches in the yard and no place to put them. And Amber thought that I had sort of maybe killed the trees, which I didn't. I mean, they're not budding yet, so we'll see whether they actually survived. They're certainly not hitting the FedEx truck anymore. But what was I going to do with all these branches and fitting them in this tiny trash can? I didn't want to load everything and go to the dump, though in retrospect, that would have been a lot less time consuming. I got out the pruning shears and I decided to just clip all the branches into tiny little bits that would fit into the garbage can. So like 5 hours later, I finally finish, and I'm right-handed, and my right hand from doing all of the clipping was just really, really sore. I was sort of walking around carrying it for the rest of the day. I didn't go to the workout I was supposed to go to on Wednesday because it was an upper body day, and I was worried that while doing the various things, I was going to actually lose grip strength and kill myself by dropping something on my head. I don't know what the moral of the story is other than there was a better way. So study smart, not hard is maybe the lesson. I don't know. Okay, we probably have more than 3% charge, so end story time. What do you predict happens if you, experiment number 2 is let's keep methyl iodide concentration constant, but vary cyanide. What do you predict if this mechanism is operative? What is your prediction? Should stay flat. And why? It's not involved in the transition state of the rate determining step in this hypothesis. So if this hypothesis is correct, we should observe that. Okay? This is our prediction. Actually, the plot thickens though. Dun, dun, dun. Actually, we observe I'm trying to gasp. It doesn't go very well in a mask. We observe, we observe linear dependence on cyanide concentration 2, which means a better rate law for this reaction would be rate equals K times methyl iodide. I should write that the same way I've always been writing it. I think the reason I told you guys about my decreased grip strength is still I'm like shaking up here as I'm writing frantically with the pencil because I guess I need to do more. I need to get one of those things you could get, used to be as seen on TV, these little things you could squeeze in the spring and the whatnot. All right, better rate law would be one that includes terms for both methyl iodide and Cn minus. This rate law would be first order or linear in methyl iodide. It would be first order in cyanide concentration. And overall, we would say it is second order because there's 2 concentration terms in the rate law, and we would call this a bimolecular reaction. Okay. So our observations are inconsistent with scenario 2, where we break one bond and then make the second. So now we need to talk about the third scenario and see whether it's consistent with our observations. We don't like the first scenario because it's bogus and involves a crazy intermediate, so we need a third option, and that's where we're going to go. So in the third option, we do both at the same time. And actually, this option is going to look kind of like the average of the first 2 options. In this mechanism, you would go directly from starting material to products through a single transition state, and you would be breaking the carbon iodide sigma bond at the same time as you are making the carbon cyanide sigma bond. And so a reasonable transition state might involve a carbon where the carbon iodide bond is lengthening but not quite broken. The carbon cyanide bond is getting closer but not quite formed yet. Probably the other substituents are evenly spaced between the thing that's leaving and the thing that's coming in. If you look at this transition state versus what we saw before, this transition state actually looks a whole lot like that bogus intermediate we proposed up top with scenario 1, only we're saying that these bonds aren't really formed, they're quite long. Right? And the intermediate also, the transition state also looks, at least on carbon, a lot like this carbocationic intermediate, only there's no full positive charge because the thing that's leaving and the thing that's coming in are both sort of nearby. The real difference in terms of structure is we're saying this is at an energy maximum, and there's no intermediate. So let's, in terms of the energy diagram, because it's only one step, this is actually pretty easy. All it involves is remembering that products are lower in energy than starting materials, and transition states are higher in energy than starting materials or products. Why is that transition state higher in energy? Because of the electron-electron repulsion that happens. Even though these bonds aren't totally formed, you've had to reorganize from sp3 hybridization to something like sp2 at the carbon, but it's not even really great sp2 hybridization because you've still got electron density here and here. So there is some repulsion that makes this transition state higher in energy. The rate law we would predict here is going to be the rate, I guess we don't need the word law in front of equals. The rate law should be linear in methyl iodide and linear in cyanide. And this is actually consistent with what we observe. Okay, go ahead.
So if it does that whole transition state, wouldn't, if there were other atoms other than just hydrogen, wouldn't it change the stereochemistry on where there are in relation to each other?
Really great. Yeah, if there were other atoms besides hydrogen here is the question in class, would there be a change in stereochemistry? And the answer is yes. If this were a stereocenter and we used Cn- and it went through this mechanism, you would expect Cn to come in opposite from where the iodide was. And that is a definite consequence of this kind of reaction mechanism. And so there'd be stereochemical evidence too, had we chosen our starting material correctly. Okay, other questions? Go ahead.
So would that make the energy maximum even greater then?
The question here in class is, if I had other non-hydrogen things on this carbon, would that make this energy maximum even higher? Because it would be more sterically crowded, the answer is yes. Yep. Okay, so in the first hour when we talked about this, there was some concern about how do you know in the absence of data whether the reaction mechanism should be 2 versus 3. And the answer is, of course, before we did the experiment, we didn't know. Experiments tell us the way the world is, and then theories are for trying to rationalize why the mechanism had to be that way. The simplest answer for why this reaction, as I've shown you, proceeds through mechanism 3 instead of 2 is that 3 is the lower energy pathway for this set of molecules. And in this way, you can think of molecules as being lazy versions of yourselves trying to decide which hill to go over. As long as you don't care about your destination, you're going to choose the lowest, the hill that is easiest to get over. And in that same way, the mechanisms that we usually agree on as organic chemists are the ones that proceed through the lowest energy transition states. So what we're saying for this particular reaction that we started talking about is that options 1 and 2 are just too high in energy to be reasonable. Option 1 for what we've described. Option 2, the energy of this transition state and this intermediate are related to the energy of the carbocation. Some carbocations we'll see are more stable than others. So we will see some starting materials and some carbocations where this is actually the lower energy pathway, but not for this material. It turns out this methyl carbocation is pretty unstable, and so it's actually too high in energy, too slow to go through this pathway versus the one that's consistent with what we observe. On the other hand, there will be things that we can do to the starting material that will make this intermediate this transition state sterically crowded and too high in energy to get to. And in those cases, scenario 2, mechanism 2 will be the preferred one. And we're often going to see that the same things that make transition state down here for mechanism 3 higher in energy are many of the same things that make the intermediate in the stepwise mechanism low enough in energy to be reasonable. So the two options 2 and 3 that I've shown you today, the unimolecular option 1 is called a substitution reaction. The N here is for nucleophilic because you have a nucleophile doing the substituting. And the 1 is for the fact that it's unimolecular. So that's the Sn1 reaction. And then the second one, where the rate law is second order or bimolecular, this is called the Sn2 mechanism. And already you guys are previewing many of the issues that are going to be important for deciding in a particular substitution reaction what is the most reasonable mechanism. We're going to learn fundamental principles derived from observations that are going to give you the ability to predict with a fair amount of accuracy which of these two mechanisms should operate based on the situation. And I guess that's about all we have time for today, so stay tuned and I will see you next time.